gas laws. So, as I told already, gas laws are the ones which will explain us about the behavior of gases under the given conditions of temperature, pressure and volume. This gas laws, the first one is Boyle's law. First of all, here let me make it very clear that all these gas laws are experimental findings. Experimental findings. Based on the experimental findings, the laws have been given to explain the behavior of gases. They are not theoretical, they are all experimental findings. From the experimental observations, these laws have been framed, and first such law is Boyle's law. Robert Boyle has given this law based on the observations what he made for a given amount of gas at constant pressure. The observations are that for a fixed amount of gas, say certain x grams of gas or n number of moles of a gas, any fixed amount, maybe 10 grams, 100 grams or 1 mole, half mole, any amount of gas. For a fixed amount of gas at constant temperature, that means the temperature of the gas is kept constant. At constant temperature, it is observed that pressure exerted by gas is inversely proportional to volume that it occupies. Again I repeat, for a given amount of gas at constant temperature, the pressure exerted by the gas is inversely proportional to volume it occupies at that particular temperature. P is inversely proportional to V, or P is proportional to 1 by V. So, when P is proportional to 1 by V, obviously we can write that this P is equal to some constant K by V, P is equal to K by V, right. Or in other words, what also you can write is that PV is constant, or for same gas at two different temperatures, T1 and T2 Kelvin. If the pressure is P1 at T1, volume is V1, then pressure at temperature T2 is P2 and volume is V2, then also we can write from this as P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2 is a what we call, what it is defined in Boyle's law, because here PV is constant. So, what you can understand is that if the P is increasing, V is decreasing, but PV remains constant. So, if P increases, V decreases, or if P decreases, V increases, but overall the product of P and V always remains constant as long as the temperature is constant. But if the temperature is changed, that T1 to T2, then of course P1 V1 is equal to P2 V2, right, provided the amount of gas is fixed, right. And the graphs if you draw, from this also, otherwise what we can say is that as P is equal to K by V, so from that what I can write is dou P by dou V at T is equal to minus K by V square. This is another way you can also tell the Boyle's law, because P is equal to K by V. That means differentiate pressure with respect to volume, dou P by dou V at constant temperature. So, dou P by dou V at T is equal to minus K by V square. This is another way of writing all these are P is proportional to 1 by V, P is equal to K by V, PV is constant, P1 V1 is equal to P2 V2, dou P by dou V at T is equal to minus K by V square. All these are the different ways in which we can describe the Boyle's law, or rather this is the way in which Robert Boyle has explained the behavior of an ideal gas. And remember, whatever now we are saying, this is all is applicable for an ideal gas, only for ideal gas. What is ideal gas? That later we discuss, but remember that this is only for ideal gas. Now, to explain this to explain this Boyle's law, or to explain this mathematical equations, again we also explain this by drawing the graphs. With the help of graphs, we can understand more clearly about the behavior of gas, or about the change in pressure and change in volume with respect to one another at constant temperature. So, the next we draw the graphs for P versus V at constant temperature. Okay. Now, first the graph for Boyle's law, or what in general we call them as isotherms. Isotherm means graph drawn at constant temperature. Any graph that is drawn at constant temperature is what we call isotherm. Now, for this Boyle's law, as we told, for a given fixed amount of gas, it is an exponential decrease as P is proportional to 1 by V. So, as the pressure is increasing, volume is decreasing, or as the pressure is decreasing, the volume is increasing, right. This is what we take it. Now, also we can draw for different gases. If you draw the graph, then, or rather for same gas, if you draw these graphs at different temperatures T1, T2, T3, then the order is that for a given P, at temperature T1, this is the volume, this is V1, at same temperature this is the volume V2, same temperature at same pressure for temperature T3, this is the volume V3. From this you can understand PV1 is less than PV2 less than PV3, it means T1 less than T2 less than T3. So, T1 less than T2 less than T3 is the graph. So, for same gas at 3 different temperatures, if you draw, these are the kinds of graphs that what we get, from which T1 less than T2 less than T3. So, you can understand at a given temperature for a given pressure what is the corresponding volume, that from this graph directly you can determine, right. And this is now also what you can write the similar graph PV versus P, as we told it that at any pressure PV is constant, because increase in pressure decreases the volume, but as already we told, at the given temperature PV is always constant. So, PV versus P, when you draw the graph, this is how we get the graphs at again the temperature T1, T2, T3. Here once again it is T1 less than T2 less than T3, right. So, this is the graph. Then another graph for Boyle's law is, when you draw for PV versus 1 by V, because it is P is equal to K into 1 by V. So, when you are drawing it for P versus 1 by V, it is a graph that what we will get at a straight line passing through origin. It is y is equal to mx time. So, this is another graph besides the other two graphs that what we have seen, that any of this. So, the different isotherms here what we are drawing are 1 P versus V, 2 PV versus P, P versus 1 by V. These are the normal three types of graphs by which this Boyle's law or the variation of pressure with variation of volume for a given fixed amount of gas at constant temperature, the behavior can be explained, right. The next what we discuss is Charles' law. Charles' law is the next one which we have to discuss regarding to explain the behavior of gases. According to Charles' law, for a fixed amount of gas, at constant pressure, now it is at constant pressure, volume occupied by gas is directly proportional to its temperature in absolute scale. For a fixed amount of gas at constant pressure, volume is directly proportional to its temperature in absolute scale. Means at constant N, that is number of moles, and pressure, volume is directly proportional to temperature. This is what the Charles' law is. Actually, this particular law, this Charles' law has been framed from one particular kind of observation. What is actual observation is? Actual observation. The actual observation is that for every 1 degree Celsius rise in temperature, for every 1 degree Celsius rise in temperature, the volume of gas is found to increase by 1 by 273 times to its initial temperature. For every 1 degree Celsius rise in temperature, the volume of a gas is found to be increased by 1 by 273 times to its initial volume. That means, for example, at T degree Celsius, if it is Vt, and at T plus 1, the observation is Vt plus Vt by 273. That means at T plus 1 degree Celsius, it is Vt into 1 plus 1 by 273, means 1 by 273 times it is increased, right. And this is what is actually the volume expansion with respect to temperature. So, from this actually, so that means what actually the observation at constant pressure, for every 1 degree Celsius rise in temperature, volume of the gas increases by 1 by 273 times. So, that means as the temperature is increasing, volume is also increasing. That is what we wrote, volume is proportional to temperature. As the temperature increases, volume is increasing. But in the this as the increase is 1 by 273 times, so this is where actually the need of temperature of absolute scale is found to be necessary. So, for every 1 degree Celsius as the fraction is 1 by 273 is increased, or for every 1 degree decrease, the volume is decreased by 1 by 273 to its initial volume. So, then the thought that came into the mind is that then by rising temperature by 1 unit, how is it possible to volume also to increase by 1 unit? So, that means how to adjust this Celsius scale into a different scale, so that for every 1 unit of increase in temperature, volume also increases by 1 unit. This has led to the discovery of the temperature scale called absolute scale or Kelvin scale. So, from this what it was then given is that in Kelvin scale the temperature is equal to 273 units more than the normal, that is degree Celsius. So, this is this 273 now if you add, then automatically this comes out to be 1 unit increase. So, it will become 2 VT, right. So, is the reason that now it is increased by 273, right. Okay. Now, here for this again the different forms in which we can write this Charles law, the different ways this law can be written, or the mathematical equations can be given to explain this law, and again what are the different graphs that we can draw for this Charles law. With respect to this Charles law, what are the different graphs that we can draw, so that we can understand the behavior of gases with respect to their volume temperature relation, right, that we see in the next. So, in this Charles law, according to which V is proportional to T at constant pressure. First of all, like the graphs that are drawn at constant temperature are called isotherms, the graphs that are drawn at constant pressure are called isobars. The graphs that are drawn at constant pressure are called isobars. So, as V is proportional to T, so also what you can write is that V is equal to Kt or V by T is equal to K. This is another way of writing the Charles law. Or from this, at two different pressures, of P1 and P2, volume of V1 and V2 and temperature is T1 and T2, then V1 by T1 is equal to V2 by T2 or V1 by V2 is equal to T1 by T2. This is another way. Or also you can write, because it is V is equal to Kt, dou V by dou T is equal to K at P. Dou V by dou T at P is equal to K. Change in volume with change in temperature at constant pressure is equal to K. Okay. Or as the V by T is equal to K implies V by T square is equal to K by T, or V by T square minus K by T is equal to 0. This is another way of giving the Charles law. So, all these are the different mathematical forms in which we can explain this Charles law. Now, we draw the graphs for V versus T at constant pressure. So, as V proportional to T or V is equal to KT or V1 by V2 is equal to T1 by T2, all this graphically we can show as first of all, if the graph is drawn for volume versus temperature in degree Celsius, then the graph what we will get is that, because here what we told is that for every 1 degree Celsius rise in temperature, volume is increased by 1 by 273 times of its initial volume. So, that way if you take it up, this is a graph for V by V versus T in degree Celsius, and this is your minus 273, right. Then, so if again this particular what do you call this minus 273 here, what we are giving, this indicates that Vt plus 1 is equal to Vt plus Vt by 273. Okay. Then V versus capital T, that is Kelvin, the graph how to draw, what we will get, that we see next. Now, V versus T, T Kelvin, volume, change in volume with change in temperature. This again, if you look at it, at a particular volume, this is T1, T2, T3. So, here at same volume at 3 different temperatures, T1, T2, T3, as T1 is less than T2 less than T3. So, at constant pressure, as V by T is constant. So, V by T is constant and T1. So, obviously what you can understand is P1 greater than P2 greater than P3, right. At 3 different pressures when you draw, then this is how you will get, and this is how you can compare the pressure. And also what we can get is that as V is equal to Kd, log V is equal to log K plus log T. So, from this again log V versus log T, when you draw the graph also you will get, and of course then in that case slope you will get it as exactly and this intercept is equal to log K when you draw it for log V versus log T. So, these are the graphs called isobars that we can draw for to explain this Charles law, that is the relation between volume and temperature of a gas at a constant pressure. Okay. The next what we look into it is the pressure temperature relation and also the other law called Avogadro's law. Now, the next is pressure and temperature relation is same as volume and temperature relation for a given gas. This is also what we call Gay-Lussac's law. According to which at constant volume P is proportional to T, absolute scale. At constant volume, pressure is proportional to temperature, just same as at constant P, V is proportional to T. Therefore, P is equal to KT, or P by T is equal to constant, P1 by T1 is equal to P2 by T2, or P1 by P2 is equal to T1 by T2. Exactly everything is same as we did it for V proportional to T, and the graphs are called, or here for every 1 degree, for every, the observation is for every 1 degree Celsius a rise in temperature of a gas at constant volume, its pressure increases by 1 by 273 times to its initial pressure. So, which is nothing but again P at T plus 1 is equal to Pt plus Pt by 273, and the graphs that are drawn called isocore, and isocores are same as isobars. Graph that is drawn at constant volume are called isocores. Isocores of a gas will be same as isobars. Again, we need not to draw it exactly the same way, everything is same, the way that we explained for the Charles law, where we have drawn it for V versus T. Now we draw P versus T, and the graph is the same thing. The next what we have is Avogadro's law. According to which at constant temperature and pressure, two gases of same number of moles will occupy same volume, or equal volumes of gases will have equal number of moles. So, this is a relation that is given for the volume versus amount of gas. As long as the temperature and pressure are kept constant, equal volumes of gases are found to have equal number of moles, or in other words, a simple way of understanding it is nothing but as long as the temperature and pressure are kept constant, if volumes of two gases are same, that means the amount of gas, the number of moles of gas, the quantity of the gas that is taken is also the same. Or if you take the two same quantities of gases, same quantity of two different gases if you have taken, then if you maintain the pressure and temperature constant, obviously then the volume occupied by both the gases also will be same. So, it is a direct relation for at constant pressure and temperature, volume of a gas is proportional to number of moles, or V1 by V2 is equal to N1 by N2. Okay. So, and from this is from where also what we understand gram molar volume. What is gram molar volume? This is gram molar volume, which also we require to understand. What the gram molar volume says is that at STP means 1 atmosphere pressure and 273 Kelvin temperature, that is 0 degree Celsius. For 1 mole of a gas, for 1 mole of ideal gas, again as I told you already, all what we are discussing is applicable only for ideal gases. For 1 mole of an ideal gas, volume occupied by it is equal to 22.414 liters. This 22.414 is what we call it as gram molar volume. It is the volume occupied by 1 gram mole, means Avogadro number of particles or weight equal to gram molecular weight, right, at 1 atmospheric pressure and 273 Kelvin. So, all the 4 laws will give relation from one parameter to the other parameter by keeping the other 2 parameters constant. Okay. So, with this all the gas laws are completed. Now, using all these gas laws, we derive one equation, we explain one equation called ideal gas equation, which gives the complete relation of one parameter over the other and will give us the clear picture about the behavior of gases under given set of conditions.